All right, let's go ahead and finish up lecture 25, which today we're basically going to pretty much finish the course. So today we're going to talk about some last two application areas, and which are basically this filter design using FFT, a useful trick when you're not using FFTs to do difference equations of filters called the interpolated Furr filter. And our last topic today will be the spectral analysis. And I think on Monday coming up, there'll be a very short session. We'll just talk about the final exam. Any questions you have, email them in if you have any questions, and I'll try to answer them in class on Monday. So it should be a short session on Monday. All right, so let's finish up our design example last time. So as a reminder, we were designing a filter, and it was an FIR filter, and we were comparing it using Hamming window FIR versus a Chebyshev type 2 filter, because we haven't really talked much about why did you choose one or the other. We just talked about here's how you do it. So this is sort of a bake-off between those two techniques. Now, given these specifications, a cutoff frequency of 0.6 pi with 60 dB of attenuation, if you go through MATLAB or some equations, you'll end up with a 9th order Chebyshev type 2. But the Hamming filter is 55th order, so that seems like it'd be significantly more computation, which we'll see is not completely the case, really. So our frequency responses, I wanted to plot them just so you can kind of see it really is apples to apples. These filters work really about the same in probably 99% of applications. So now implementation. What does it cost to actually do this? So let's start with the infinite impulse response filter. So we're going to implement this using a difference equation. And if you recall, the difference equation had a form like this equation here, where we have certain A coefficients and certain B coefficients. Since it was a 9th order filter, we have A0, A1, A2, up to A9. And A0 is a 1 coefficient, so it kind of doesn't count. And the B coefficients basically weight the input data. That's B0, B1, ... up to B9. So we really have 10 A coefficients and 10 B coefficients, but one of the A coefficients is really 1. So 9 plus 10 is 19. So if you had complex data coming into your system, that'd be about 19 complex multiplies per output sample, right? So every time we calculate a YN, we have to do 19 multiplies and then 18 adds. So that's sort of the bill for doing that. Now we wanted to compare that to what's our FIR filter. And to kind of get started, I wanted to suppose you had a 512-point efficient FFT engine available. Different choices are possible, and it will influence the results a little bit, but let's just start with that. So with that going forward, we know the FIR filter has the 56 B coefficients in the MATLAB parlance in order to implement it. So we're going to basically do 56 multiplies to get the output. Right, so it'd be 56 multiplies 56 adds every time we wanted to spit it out if we were doing a difference equation, but we're not. We're going to use an FFT. So let's think back to how the overlap save algorithm worked for the block convolution. And if you recall, in our case, P, which is the impulse response length, is going to be 56. And so each section of data that we're going to process is going to overlap with its neighboring section by P minus 1 samples. So what does that mean? That means we don't have 512 new samples to process. We have 512 minus the 56 minus 1, which is 457. And if you also recall from that algorithm, the first P minus 1 are aliased anyway. So after you do this whole FFT processing, those first ones are aliased, you throw them away anyway. So what do you really get out? Well, it's the 512 minus the P minus 1. So in our case, we get 457 output samples, which is quite a few output samples, but we do have quite a few complex multiplies to do as well. Now we're going to go through this and just kind of tally it up and assume that the FFT requires n log n, which many of them actually require less than that. So this is kind of an upper bound on what it would cost. So to do that, how does it work? Well, first of all, we have to get a buffer of data, so we have to get a section of data in, the 457 new samples, right? Because we have the overlapping samples, which are from the previous section. So We had those together in a buffer, so we got a length of 512. We do an FFT, and that requires n log n. But we have to multiply that times what? The FFT of the filter impulse response, because we're doing the circular convolution, I guess, using I guess FFTs do circular convolution, but we're making the FFT length long enough to do linear, right? So we end up with a 512-point FFT impulse response here. And so basically, you think to yourself, all right, offline, I calculated 56 coefficients, or 56 different weights for that FIR filter. So then I do a 512-point FFT and save that in memory somewhere. So that doesn't cost me anything, because I did it one time and I never do it again. So that was free. This part's free. But every time I get new data, I have to take an FFT and I have to multiply it. So everything coming in here is new. So this multiplication costs. It's new data every time, right? So that's 512 complex multiplies. And then once we're done, we got an inverse FFT. So down here on this line, we just add it all up. 2 times n log n plus another n, which is 512, gives us the 9,728, but we get 457 outputs. So we just divide it out, 21.3 complex multiplies per output sample. So not really a lot worse than the other one, which was 19, right? So for this simple example, let's just draw a few conclusions. So if we use a 55th order filter, that's 21 roughly complex operations per output sample. And we always have to boil this down to operations per output sample. You have to have some metric to be able to compare it, because every time you get a new set of input samples, you got to keep up. So one of the metrics we use is complex operations per output sample. Ninth order IIR filter, we could just count those up. That was pretty easy, 19. Nice thing about FIR filters, we talked about earlier, it has guaranteed stability in linear phase, which is usually a nice thing to have for many applications. And of course, you can change that FIR filter and make it, you can, I guess, increase the order easily. You can do a lot of things with it. It's easier to design those, and so in some ways you can have a little more flexibility. The IIR has slightly less complex operations per sample, no question about it. You still gain a little bit. Of course, in this example, I did kind of cheat and say that the FFT was n log n, where I think if you go through the book, the radix 2 is n over 2 log n. So slightly less, really. And then radix 4 algorithms, which you didn't discuss at all, even more efficient. So this is kind of a gentle introduction and an upper bound on how good it could be. So we've got kind of everything summarized here. If we use the difference equation, not a good idea unless you have plenty of complex multiplies to spare. Using FFTs, you don't use an FFT to do this. You probably could figure out a way to do it, but not doing that. So let's see. What's the trend? Okay, trend diagram. What I wanted to do here was kind of show you that even when you change that FIR response, it's not going to cost you that much more. Like for instance, here's an example. We went through this, and let's say we pulled out our hair and said it's going to take 56 coefficients. Oh my goodness. Well, we finally make it work. Then we turn around and come back and find out later that's not going to be good enough. It needs to be 80 coefficients or 100. You know, that could be bad. Or if it was the 19 complex multiplies for the IIR filter, 9th order Chebyshev type 2 won't do it. We need to be 18th order. Well, that doubles it right off the bat, right? So if you're changing the order of the filter by a factor of 2, you've doubled it for the IIR filter if you're implementing it in the difference equation. So that's kind of the introduction to this chart. So let's look over here. And on the x-axis, I put the impulse response length. So for us, that was 56 for our simple example. And here I put the minimum operations per output sample. And what do I mean by the minimum operations? That means what I did, and it's been a while since I've done it, is I went and I said, okay, let me try different size FFTs that are all radix 2. So, 128, 256, 512, 1024, 2048, etc., etc. And using those with this impulse response, what is the minimum amount of complex operations I can use for that impulse response length? Because remember, it's going to depend on the length of the impulse response, right? Because I think as we went back, what did we calculate? It's what, this 9,728 complex multiplies over 457 outputs. What was the 457 output? That's your NFFT, the size of your FFT minus the impulse response length. So that plays into this complex multiplies per output sample. So if you look at this chart, where were we? We were like 56 up here. So yeah, right in here around the 21.3. But let's suppose instead of 50, it was 110. So now we're up to 23 with the right sized FFT. So not much more. So that begs the question, well, what size FFT? So that's why this chart comes in over here on the right panel. So let's look at ours. If we did a 56-point impulse response, that puts us right in at 512. So I happen to choose a good one for our particular application. But if we wanted to go up to 110, well, then we'd need a 1024-point FFT. That's the one that gives you the minimum number of complex operations per output sample. So I guess, let's see, do I kind of, whoops, I guess we'll just stop here and say that hopefully you can kind of see that just doubling, like from 40 to 80, the impulse response length did what? It moves you from about 20 to 22-ish. So what happened? It increased our number of ops per output sample by about 10%, and we doubled the length of the filter, or doubled the order of the FIR filter. If you do that for the infinite impulse response filter, what happens? It's 100%, right? You doubled the order of it, so you get twice as many A and B coefficients. So hopefully this kind of gives you a feel for kind of the games you can play in terms of trying to account for the number of complex operations and sizing all this stuff. So that kind of brings us to our next topic here, which is the interpolated FIR filter. Now, all the stuff I said before was, okay, that's great if you have an FFT, but what if you don't? What if all you've got is digital logic that you're programming in some way with a programmable logic device or something very simple, and you really don't have an FFT-like engine, and you don't have the resources to even code one up inside the amount of logic you have, or you're limited in some way like that. So what you're going to have to do is do a difference equation. So suppose, what tricks can you play to still use a difference equation and still get some gains in computational efficiency? And so that brings us to the interpolated FIR filter. So we're going to implement, and I guess here's the rub, we're going to implement an FIR filter with a difference equation and do it more efficiently. So here's the example I'm going to take. And this is not drawn to scale. I'm going to sketch it on the pad here, but imagine we're going to use that Kaiser window filter spec design. So remember the Kaiser window, the nice thing about using that is it had kind of a bunch of canned equations and recipes, and you could just kind of go through and fill in the blank, and it would tell you the order of the filter, and it'd tell you how to calculate the coefficients. And so it was kind of nice to use. But suppose we had a pass band of pi over 100 and a stop band of pi over 50, and this delta S of 10 to the minus 3. So I have a little cartoon here that shows kind of what that looks like. That's our desired filter. But I wanted to, in case you lose it, let's see, looks like something is weird here. Let's just do this. If we were really going to look at this, maybe I should try to get it straight. What does this layer look like? It really looks like something kind of like this. Right, so just a sliver of passband. So it's a very narrow low-pass filter. And the transition band is what? Pi over 100 is the passband, plus another pi over 100 would be what? 2 pi over 100 or pi over 50. So the transition band is also very narrow, pi over 100. So that's, I kind of wanted to redraw it for you because my cartoon doesn't quite do it justice. So you kind of see this is a somewhat weird situation right off the bat. We need a very narrow filter, very sharp transition region. So hopefully that's alerting you right off the bat, this is going to be a high order filter. So with that in mind, let's just crank through the equations and see what happens. So I think one of the quantities is delta W, which is that stop band minus the pass band, which is pi over 100. And then there's other quantity A, which is kind of the attenuation needed, which is minus 60 dB. Then we plug it into the all-important M equation, which is the order of the filter. So that's, for our case, I think M is this form. So you just plug and chug. You get 724.4, so you have to round that to an integer because M has to be an integer, so you get 725. So the order of the filter is 725. So that seems pretty high, so that means you're going to need 726 coefficients is the length of the impulse response. So sometimes that might just be a non-starter right off the bat. I might say, no, go back and rethink that. That's just too much. So what do we do? Well, lots of coefficients. It's going to give you lots of complex multiplies, right? So what's done here is a pretty sneaky trick where we basically do it in two stages. So H of n is our desired filter. So as we go through this, think H of n is our desired filter. And what we're doing is we're kind of making it, the output is really the convolution of our P filter and Q filter. So if you convolve P with Q, you get H of n out. Now this might be a little weird to you because you're thinking usually we convolve an input signal with an impulse response and get an output signal. Well, now we're convolving one weird filter with another weird filter and getting the desired filter. So we're kind of doing a kind of a trick like that. So how does this actually help us? Well, as it turns out, the P of n filter is just an upsampled version of a G of n, which, what is G of n? Well, G of n is a new filter that's lower order and easier to implement. So, okay, so we're going to get a lower order filter that's easy to implement. We're going to upsample that, and then we're going to filter it with another filter, Q of n, which gets rid of the images of P of n. And so if you remember back when we did upsampling, what happens? You have some signal and you upsample, kind of smashes everything down. Everything gets narrower in frequency space. So and then we end up with images, and then we have to filter them out with upsampling. Same thing happens with this filter impulse response. So let's talk a little bit about the magical G of n. Where does that come from? So it's kind of an engineering choice that you'd make. You'd probably go through and look at the resources you have and how easy this is to do, what the payoff is. But for our example, we're just going to choose specs for G of n that are basically 10 times easier to meet. So instead of pi over 100 as the pass band, we're going to make it pi over 10. Instead of pi over 50 as the stop band, it's pi over 5. So everything's kind of spread out now and a little bit easier to meet. And why is that? Well, now the transition band is pi over 10 instead of pi over 100. And when we plug this into our equation for m, we get 73, which kind of makes sense, right? It was almost 700 and, what was it, 725, 723. So you take divide that by 10, about 73. So you can almost kind of see how it would work out. The transition region is 10 times wider. You need a filter order that's 10 times, factor of 10 less. So next step. All right, we've got our G of n. And I wanted to put this little slide in as a reminder what happens when you upsample. Right? We're getting G of n, which is our easy to design filter. We're upsampling it to get P of n. So if you recall our upsampling identities, the frequency response, or the spectrum of P, or the frequency response of P is equal to G scaled by this factor of 10, right? So how does that affect things? Well, if we start with G, which is our easy to design filter, and we have copies every 2 pi, and has a passband of pi over 10, and a stop band of pi over 5, and it's repeating and repeating. This is our starting point, but now we upsample and inject basically 9 zeros between every sample. What happens? It smashes everything together, which just so happens to help us out, right? Because now this weird filter that was 10 times easier to design all of a sudden becomes, hey, that's the filter I wanted to design to begin with. That's what we actually want. Now, we're not done yet, because what happened? We've got all these copies over here. Copies that were now sitting at 2 pi are now sitting at 2 pi over 10. So right here, this is kind of a zoomed in version. So I think the next slide is a zoomed out. Yeah. So now let's back away so we can see everything from minus pi to pi. And now we see all those copies in here. And the desired filter response is right in here. So we've got P of ej omega. It's this entire thing, and we only want one of those copies, right? So what would happen if we used P of n to filter something? Well, one of the key points of all this is that this P of n that we calculated, remember, has 74 non-zero coefficients. And we've injected, since we're upsampling, basically by a factor of 10, 9 zeros between every coefficient. So you might think, well, it's still about the same number of coefficients as the other filter. And it is, except what's the big payoff? Smart hardware won't multiply by 0 and add these. So if you had any type of hardware implementation you were building, if a 0 was loaded into that register, it's not going to multiply that times it. It's just going to say, I'm not going to multiply and add the results of this, we're just going to skip it. So those aren't going to cost you as multiplies. So we've got our P of n. We know it has this weird property. So what do? We get rid of the images by going to a Q of n, right? So how do we do that? Well, we're just going to filter the frequency response of P ej omega as if it was a signal, and we need to get rid of those images. So now we just need to design a new filter to filter the filter, right? So let's jump back in and zoom back into P ej omega and say, all right, this is the one I want right here with a passband of pi over 100 and a stop band of pi over 50. But the problem are these copies, nuisance copies. So now I'm going to design a new filter, Q of ej omega, which does what? Well, in the passband of this Q filter is, guess what? The filter I really want, H of n. And what's in the stop band? The stuff I don't want, all the images of that filter. So now we're going to design a new filter, Q of n, and notice that it has a cutoff frequency at 9 pi over 50. And a pass band is what? Pi over 100. And so the reason why this whole thing even works at all is because this transition region here is fairly wide. If it wasn't, then it wouldn't buy you anything, because then you have a high order filter again. So if you were playing with this on your own to optimize it, you'd kind of figure out, okay, what sort of upsampling do I need in order to sort of maximize this distance, because it's kind of a trade-off. You want to maximize this and not make and still meet your filter specs here. So it's kind of, I think, a trade-off. So let's go through that and try it. So now back to the Kaiser window filter calculations now, but for Q of n. And so down here I've drawn our Q of n we want. We still want a passband of pi over 100, but now we want 9 pi over 50. Why? Because that's the first image of that weird interpolated filter, P of n. So by putting this in here, we get a transition of 17 pi over 100. We still want minus 60 dB. We crank it through the equation, get 42.6, so 43. So length of impulse response n plus 1, which is 44, but I wrote 43. Not that it matters, but it's about, looks like that's one off. So now we end up with, well, we've got three filters in play in some sense. We've got H of n, the thing we wanted. Then we've got G of n, the thing that's 10 times easier. And then we've got P and Q of n, right? And we've gone through the Kaiser window filter calculations for all of those. So let's summarize. Our original implementation, I sort of put a blue background on it. So we have X of n comes in, Y of n comes out, 726 coefficient FIR filter. So 726 multiplies because we're doing this with a difference equation. And that's what sort of made us think, goodness, is there a better way? Then we used the interpolated FIR approach. So we ended up with saying what's 10 times easier to implement and upsampling it. And so that added a whole bunch of zero coefficients, and we called that P of n. And P of n was great. It had one of the images in it was the filter we wanted. Unfortunately, it had a whole bunch of other stuff we had to get rid of. So that told us to design Q of n, which had 44 coefficients. So if we add these together, 74 plus 44, it's 118 multiplies per output sample. So we've kind of cut it down by a factor of 6 or so in terms of the computation. So kind of a useful trick when you need it, when you can when you're forced to use a difference equation. So let's see, is there a summary here too? So, all right, so implementing that FIR may be too resource intensive. We can do this, and I guess the key part is the smart hardware does not execute multiplies by 0. If it did that anyway, then it wouldn't buy anything. So, and it, of course, exploits that frequency domain effects of upsampling. And I think that is all there is to that. Yep. All right, I think that brings us to last topic. So the last topic is Fourier analysis or spectral analysis. And what we're going to talk about today is trying to figure out, we have some data and we're trying to figure out what the spectrum is of that data. And what are the techniques that we use to determine that spectrum or to analyze that spectrum. And this is deterministic spectral analysis. In other classes you'll learn more about statistical methods. But here we're just going to kind of get the basics and develop some more intuition of what you have control over, what you need to avoid, and how to, I guess, get around doing the introduction to spectral analysis. So typically how this might work is you'll have some sort of system, a communication system, a radar signal, some kind of signal that's of indefinite length. And we'll see kind of how the length affects things in terms of the windows that we can use later, but that's an important piece in all this. And we have an anti-aliasing filter, which we've talked about before. We go into some kind of A to D or continuous time to discrete time converter type setup. And then one way to think about it is we extract some portion of this by multiplying it times a window function. And then finally, the window data, we can put it through some kind of DFT, maybe get some signal out. maybe call it V of k. So it's sometimes helpful to remember each of these steps because they all affect V of k in the end, depending on how you've done them all. So I think we'll go look at this, how this is done in the frequency domain, see if we can develop a little bit of intuition into how this plays out. So first step is this part is somewhat of a review because we know that the discrete time Fourier transform of x was just a scaled version of the continuous time version, right? Which is usually what's of interest. And that's 2 pi over t. So that's kind of a review, stuff we already know. All these things are copies because it's a sampled signal. But the key is this whole thing is now going to be multiplied by a window sequence. So what does that do to us? So the output, this output of the whole process, since we're multiplying in time, as you can imagine, we're going to be convolving in frequency. And this would be W d theta. So what's going to happen here? The convolution with this is going to basically affect the output spectrum, or the spectrum of this when you look at the output. I guess when you convolve this, sort of the sharp peaks and discontinuities in the spectrum will go away. Now if you're looking for sharp peaks and you're trying to resolve very closely spaced signals, because those have information for you, then that can have an effect and it can cause a problem. And we're going to dig into that a little bit today. So first thing is, let's look at the spacing between frequencies. So if we recall, the output, the V of k, is going to be the input V of n minus j 2 pi nk over cap n, right? Regular DFT formula. Now, let's suppose if the window length L is less than n. So let's say L is less than or equal to n. If that's the case, then we can have, I think I want it to be, the window length is equal to L. Because I want this, but I want the samples to be kind of like what we talked before. The version of this is just the samples 2 pi k over cap n. So I think that for this we want the window length L to equal n. Sorry about that. So this is all kind of a review, but now what are the spacings between it in both domains? In the frequency domain with omega, we've already got that. We just wrote it down. It's going to be 2 pi over n. But let's convert it back to capital omega, or continuous time, because usually what's happening in the physics world is impacting omega, cap omega s. That's what you really care about. But what we're playing with is the sampled data, so we have to map that back. So spacing between DFT frequencies is what? It's just 2 pi over n, right? And that was the fact that what, omega k was 2 pi k over n, where k is 0, 1, dot, dot, dot. But remember our favorite formula for relating these two, right? Omega is just a scaled version of capital omega times t. Right? Or we can write omega is little omega over t. So if we kind of look at how that impacts that formula, we could say the spacings of capital omega k is going to be what, 2 pi k all over n, but all over t. So you end up with sort of the spacing equivalence. So this can help you convert back to hertz or things that make sense in terms of the physics of the situation. Because here we're all in just normalized radian. So as an example, let's just crank through one quick example. Suppose we have a frequency or sample rate of 5,000 hertz. And we want a frequency spacing, so we desire a frequency spacing, a frequency sampling. I'm going to put spacing. In parentheses, I'm going to put sampling. Notice I'm not going to use the word resolution because that's a different topic that we'll, I think, hit on today. But it's a spacing or a sampling of 10 hertz. So what we want to do is find the minimum DFT length or size. Now this is just to get a spacing, so to some extent the number of samples isn't important, but the k factor is, as we'll talk about a little bit later. So we said omega k is what? 2 pi k all over nt. One way you could look at this is say, well, this omega 0 is 0 because k is 0. And the first one, the very first sample is omega 1, which is 2 pi, k is 1, all over n times t. And I'm looking at this, the delta between these two. Whoops. The delta between these two. That's really what's of interest here. So kind of that's what, 2 pi times 1. N we don't know, that's the thing we're trying to find. T is 1 over 5,000, right? So let's basically go ahead and say we want the difference between these two to be 10. So how do I do that in a way that's easy to follow? Subtract these. It's 2 pi times 1 all over n and 1 over 5,000 equals, we want it to be 10 hertz, but hertz is not in radian frequency, so make that 2 pi times 10. So omega 1 minus omega 0, which you could call delta omega, is going to be what? 2 pi times 1 all over 2 pi times 10 times n over 5,000. I just sort of move things around somewhat clumsily, but if you do that, that del omega is going to be I think, let's see, I wanted to get n equals 500, but I didn't want to set del omega equal to that. I just kind of wanted to show that the difference between those was n makes it more confusing to put that there. But N is the 500, and I guess we can kind of look at it by putting it back together. That might have been more of a confusing way of doing it. Maybe another way to look at it is if del F is 10 hertz, and 2 pi del F is going to be what? 2 pi times 10. Let's do it a slightly different way. Might be a little more straightforward than that way. Then we know that del omega is 2 pi over nt, and I want that to be 2 pi times 10. So moving everything over gets what? N is t times 2 pi times 10 all over 2 pi. And so that's why that times. Oh, I left my n. Forgot to put it 1 over n still. Everything else moved over. So 1 over n is 1 over 5,000. 10 over 5,000. So n equals 500. I'm not sure that was any more straightforward, but you can kind of see how the delta F's 10 hertz converted to 2 pi over nt. Gets us where we're headed, which is a DFT size of 500, or at least a data record length. So let's kind of move a little bit further into this, and I think what I want to do is kind of look at the properties of these windows, because we talked a little bit about how they affected, and I think you remember back to when we were doing filter design. PC. When we were doing filter design originally, we talked about windows. And we were doing that in the context of an FIR filter design. But now we're going to do it in the context of sort of side lobe control. So actually, let's just put that down as our first topic, and then we'll go to the slides. So for side lobe control, one of the things we were talking about was that the windows basically are going to trade side lobes for frequency resolution. And here I am using the word resolution. So what does that mean? Typically in many applications, what do we want to do? We want to, if we're looking at the spectrum, we want to find out, is something there, like detecting it, estimating it, what is the frequency of the energy that's there, and furthermore, how much different signals are there. Are there 2 signals, 3 signals, and how closely can you resolve signals? So as signals get closer and closer together in frequency, you cannot resolve them. At some point, they're too close. You will not be able to resolve the signals. Well, if you use certain types of windows, that will impact that. You will not be able to resolve the signals. It reduces your resolution. But what's the trade-off? The side lobes. And as we're going to show, if you have a very strong signal, it will have side lobes that could cover up a weak signal. And so it will impact your ability to find weaker signals, which we're going to talk about today. So windows trade side lobes for frequency resolution. In our development, L will equal the window length And first off, we're just going to talk about 2 of them as a reminder, because we talked about these before in a slightly different context. So what's known as the rectangular window. which in some ways is not like any window at all. It just means you truncated the data. I had 6 data points. I put them into a DFT. I didn't put any weight on them. They're all weighted by a 1. So no weighting, no window. What is that? It's just 1 for all samples. So this will be multiplied times your input x of n, and it's all 1s, so it doesn't affect it. Well, this has several properties. As it turns out, it has the worst side lobes, which we're going to see, which are the minus 13 dB side lobes. So whatever the main lobe peak or whatever the main energy is in the signal, it will have side lobes that are 13 dB down near it, so it could obscure other signals. So that's not so hot, but it does have the best frequency resolution. Now there are different concepts of frequency resolution, but we're going to use the null to null of the main lobe. And I think that's 4 pi over L for that, in which we're going to play around with this in MATLAB a little bit so you can kind of see what's going on. The other window we'll talk about, just as a refresher, is the Hamming window. It also has it's a family of, it's a member of one of the family of the raised cosine windows. So there are multiple ones. And I think they parameterized it to be, what, 2 pi n all over L minus 1. So a window like that. This one basically has much better side lobes, minus 41 dB side lobes. So that's usually pretty good for many applications. Maybe I'll make this bullet like that. Minus 41 dB side lobes. The resolution is 8 pi. Null to null. Resolution. So it's saying that main lobe width is that wide, so things that get closer and closer together, you won't be able to resolve them. And we're going to go through a simple example that kind of shows that. And of course, there are other windows, which you know about from previously. We're not going to go into them, like obviously the Kaiser, we just talked about it today. Bartlett, which is the triangular window. Hahn window, another raised cosine. Taylor window, used usually in array processing, but also could be used here. So let's kind of get more of a feel for how these windows work. Sorry, going to the PC here. So first off, we want to look at these windows in the time domain and the frequency domain and kind of hopefully get some intuition into how they work and why they work and their effects on the signals. So clearly this rectangular window, everything hits 1s, no problem, and this raised cosine window is the Hamming. You can see why it's called a raised cosine window, because that's pretty much what it looks like. So those are what they look like in the time domain. If we go to the frequency domain, you can kind of see the side lobes from the rectangular window are much higher than the Hamming window, which is why people would use a Hamming window, right? Now if we blow up that picture so you can see a little bit closer, we notice if we start with the rectangular window, which is the blue trace, we see that, yep, we've got all these side lobes, and the very first one is right here around minus 13. Hence the minus 13 side lobe comment. The red trace is the Hamming window, and it's down here. Its side lobes are minus 40 something. Maybe that one's minus 41, but they're in the minus 40s right here. Now, question of resolution. If we look at the rectangular window, and we kind of look at the null to null width, which, what do I mean by null to null? It's the first place as you go down the thing, the main lobe, where it hits here and goes to a null. So if we could dot 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 this down here, it's around like 0.04 or something. If we do that to the Hamming, it's closer to 0.07 or 8, so it's kind of double that. So what they're saying is signals that get closer and closer together, you're not going to be able to resolve. And we're going to show a simple example of that. But that's the main idea there. Now I think I wanted to name two sources of side lobes in the data. So obviously if you have a the data is finite length, that means that you're not going to have all the rest of the samples zero. We'll go into an example of that, but the nature of the length of the data set is going to impact the side lobes, and so is the periodic nature of the DFT. So we're going to address both these. This isn't an exhaustive list. It's just two things that we can quickly, I think, nail down and investigate in a reasonable amount of time. So let's go through that. So one way to think about this windowing operation is that you have an infinitely long sequence and you're multiplying it times this rectangular function. And that basically just extracts a portion of the signal. So if you have a continuous type of mind, you might think, okay, this signal over here in blue goes on for ever and ever. So if I take a Fourier transform of that, it would really be an impulse. A real honest to goodness, zero width, infinite height impulse. Well, we're not doing that, right? We're not taking we don't have time to take infinite data. So we'll take some windowed amount, which is this window function sort of extracts it. So we have sort of limited time support in some sense. So what does that do? In the frequency domain, you can think of it as now we've got this frequency domain spectrum that's basically a courtesy of this time domain, and it has some width. So when we convolve it with these delta functions, it very much smears them out and makes them wider. And so that's the intuition. So hopefully in your mind you can think, well, the wider I make this window, the narrower I can make my my frequency spectrums for the signals. And you can, except that as an engineer you're going to find out that making this window wider means what? It means you're taking more data, or you're spending more time taking data when you could be spending more time taking data somewhere else. So there's going to be trade-offs, involved in all this. So the periodic nature of the DFT. So when you take the endpoint DFT, kind of the underlying assumption as we went through is really this is discrete Fourier series, and really it's periodic. Now, we take DFTs of signals that aren't periodic all the time, and we don't worry about it. Well, we don't worry about it, but it does have an effect on the spectrum. Mainly we don't worry about it because there's not a lot we can do about it. But it does have an effect, which I'm going to demonstrate here. It causes the discontinuities, or the lack of periodicity, basically causes this leakage problem. What is leakage? It means that when energy in some DFT bins leak into other bins, raising the whole background, which would prevent you from seeing weaker signals. So let's do a simple example of that. So what do I mean by these periodic effects? Suppose we have a signal in red. It's a cosine signal. Now remember, when we take a DFT of it, we're assuming that it's a infinitely, it's a periodic signal. It's infinite long, it's just a periodic signal. So I basically took a copy of this and pasted it here in green and there in blue just to see, well, does it look periodic? And in your mind's eye, I'm hoping you say, well, if I just connected these 2 points, it sort of looks like the natural point after this blue point would be this red point. And then it keeps going, and the natural point after this red point would be the green point. So there doesn't seem to be an obvious discontinuity there. Well, let's see what happens when we take the DFT of the red signal. Well, when we did that, we got zeros for everything except the returns at pi over 0.25 pi, or pi over 4, which is good because that's the frequency of the signal we were starting with. So yes, everything's right with the world. That makes sense. You can kind of see we got the two peaks where we expected them, and everything else is 0. And why shouldn't everything else be 0? There's nothing else there, right? Well, let's take another example. Now, if you were drawing a cosine signal, would you expect to jump from this blue one directly to here? That doesn't look quite like a natural progression. I would think it'd look more like this side here, where it would jump up and then take a few samples to come up to the top. But when we do this with the DFT, we're sort of imposing this discontinuity. What happens when you take an FFT of that signal, or a DFT of that signal? Well, it's not quite as cute as the other one. Here's x of n is 0.589 n, and 0.589, so we're getting, well, this is in pi radians, so I have to divide it by pi. But we're getting 2 peaks, what we expect. It's a cosine signal. But notice now there's other values that are off the main peak of this thing. So why is that? Well, it's caused by this leakage into other bins. So if you can have a situation where you don't have the leakage, that's good. If you can manipulate it so you don't, that's better. But you're still going to end up with it just because of the periodic nature of it. So let's compare those two cases. When you look at the case where there's no leakage, I think this is an 8-point DFT, so you sum it up and it's 8. This one, the power isn't as high, but it's still a cosine with the same power. But if you notice, you have to add up all this side lobe power all over the place, and you get, I guess, the same amount due to Parseval's law, right? The power in both domains has to be the same. So the downside is, what do these side lobes cause? They cause you not to be able to find other signals to do spectral analysis. So that's part of the problem. So now let's do an example of a trade-off. So what I wanted to do here was show sort of one of the trades that you have to deal with when you're looking at these things. And so what we're going to do is look at, there's 2 signals happens to be in this data. And we're going to compare just the rectangular window, which is no weighting at all really, and the Kaiser window, which has 45 dB side lobes, or a Kaiser window with 45 dB side lobes. And it's basically, this is in a noisy background, but if you look at these 2 traces, in red, you can kind of see that, yeah, you can basically make out this second signal at 700 hertz, and you easily can see this one at 500. If you look at the blue trace, you can kind of both make them out too at the same time. There, you can see this blue trace, this blue peak here, etc. Now what I'm going to do is to try to show what happens by basically walking that 700 hertz signal closer and closer to the 500 hertz signal, so you can kind of see how using these different windows can affect your ability to interpret the spectrum. So as we march this thing along, things look kind of okay, but as we start to get closer and closer to the side lobes, you have to ask yourself, would you necessarily call this peak significant unless you had this nice red peak here underneath it to point your eye to it and say, yeah, there's something for real there. And as we get closer and closer, it becomes more and more difficult. Like right there is pretty sporting to say, yeah, there's a dB difference. That's really a real target or a real signal. Whereas you can kind of tell here, this is at least 10 dB, close to 10 dB above the background. And as we get really close there, it's hard with either of them. Eventually, it gets pretty tough. So the purpose of this is to kind of show you the effects of the side lobes and why you might want to use windowing. So you might say, okay, I'm sold, let's use windowing and forget about it. Well, now there's the dark side of windowing, the resolution limitations. So what we're going to talk about next is move these 2 close together and see if you can resolve them. So typically, as I walk these signals closer and closer together, you kind of have to ask yourself, what sort of algorithm would you have to design to be able to tell that there was 2 signals there or 1 signal? And with the Kaiser window, it's kind of hard to tell at that point whether there's 2 or 1. I mean, you might be able to do it if you're doing it by hand, but if you had to write a machine tool to do it, it might be more difficult. I think the rectangular window, you still stand a chance because there's this deep null between the two. So it's kind of showing you can resolve this signal here at, what, 505 hertz and 500 hertz. Whereas with the Kaiser, you really can't. Of course, you can keep going, and it gets, eventually they all on top of each other. You have the two signals. All right, so bottom line is, if you can, I mean, typically what you try to do is you try to get the best of both worlds. You just collect enough data that when you window it, you still get the resolution that you need. And then you have to live with then you can put the side lobes on it and you can still get there. So I think we'll talk a little bit about, let's see, oversampling the DFT with zero padding. That's our next topic. Okay. One of the important things that really helps with interpreting the spectrum is what we call oversampling a DFT, or zero padding. So let's talk a little bit about that. So let's go back to the common DFT formula, right? But instead of n, where n was the number of samples that you happen to have, we're now going to use NFFT. It's okay, you can go 0 to NFFT minus 1, or whatever you want. And you can get that many frequency samples. So basically, how do you do that? It's kind of the same thing as appending zeros to the end of the data record before taking the DFT. And MATLAB will do that for you. I think we already experimented with that when using it to do FFTs to help us do linear convolution. So the second argument of the FFT will tell you the length. So basically, it appends the data record in with a whole bunch of zeros to make it NFFT long. And this really is necessary for proper spectrum interpretation, as we'll show in the next few slides here. So one example is missing spectral content. If we sample this with a DFT length of 64, and this is the pi/4, it looks like everything is 0 there. Which is it? Well, it is. But here's the thing, it's 0 where we sampled it. But if we oversample it with a much larger point FFT, I used a DFT length of 8192. That's the red trace. Notice the red trace agrees with the blue trace at every sample. It really does. But there's spectral content there that you didn't know was there. So sometimes that's important for you to know, and so you might want to be aware of it. Let's see. The other case is, imagine you had a situation like this where you have basically this signal is comprised of two cosines. If you take a 64-point DFT, you get two peaks. You probably assume there's one cosine present, one signal of interest present, let's say. If you do a 8192 point DFT on that, you can see that, wow, with all those extra samples, of course it still agrees at every point with the blue trace when they line up. But now if you were running an algorithm to find peaks, you'd obviously find two peaks. It wouldn't take a real fancy algorithm to tell that there are two peaks here instead of one. So sometimes oversampling it can really help you identify and understand what you're looking at. And I think I expanded this, yeah. In the oversampled spectrum, you can really see, wow, there's a huge null there. There are definitely two signals here, and that may be important in your application to be able to distinguish. And final section is magnitude estimation. So suppose you had some signal, and you do a DFT on it, you get this, and you think, okay, well, this is the peak value, so that means something. Is that like a target, or is that a signal that I'm trying to acquire? Is it a communication signal? What is the magnitude of it? Well, if you were to oversample this, notice that actually you had a pretty significant error in the amplitude estimation, because the samples you missed, or the samples that you didn't fill in, actually added a significant amount of height to that, which then might tell you information about the signal you didn't know that you wanted, right? So if you estimate it, you might estimate it wrong. So there's good reasons to to oversample these spectrums. Helps you with the interpretation. Now, I think the last thing I wanted to look at, but maybe what we'll look at is a sample problem that one could have on a final exam. That might be the right answer here. Just trying to find. So let's see, what sort of problems as an example problem could we have for spectral estimation? So let's suppose we have a requirement that's basically saying you're going to have this data acquisition system, but it needs to be able to resolve frequencies separated by pi over 100. So it needs to be able to resolve frequencies that are fairly closely spaced. And we need to use a power of 2 DFT, or radix 2 DFT. So those are our requirements. That's the type of system we have. So what are we trying to find? We're trying to find what is the minimum window length. To meet the requirement. So how large a window do we need, or how much, it comes down to how much data. Well, we know off the bat, if we look at the Hamming window, that null-to-null resolution, I'll abbreviate resolution, null-to-null resolution was what, 8 pi over L minus 1. Well, I know the desired resolution is less than or equal to pi over 100. We need to be able to resolve signals that are separated by pi over 100. So my desired res has to be better than that. So I also know that 8 pi over L minus 1 would be my resolution if I was using a Hamming window. And it had better be less than pi over 100. That's our requirement. But we also know that L can't just be any old number. L has to be a power of 2. So L can be 2, 4, 8, blah, 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 20, 48, etc. So if we kind of solve for this, the reciprocal of L minus 1 is less than what? Divide by pi and divide by 8. So that would imply that L minus 1 is greater than or equal to 800. So what's the next power of 2 after that? Well, we know 512 is a power of 2, so L would have to equal 1024. Because that's the next power of 2 that meets that requirement. So that's a possible kind of problem one can have. Let's see. I want to do one more. Let's look at this problem. Suppose you were trying to use a rectangular window So the problem is, the second one is use a rectangular window I guess, so the question is, what L will resolve both signal components? And so let's let X of n, this is the signal we're kind of our model that we want to make sure that this system is capable of resolving it. So you kind of think of it as a test vector for your system that you're designing. Cosine of 13 pi for 60 n. So if we're going to resolve those, we need to be able to have, what's the difference between those? So LW is what? Let's subtract them and see what the difference in frequency space is between them. 60 over pi minus 5 pi over, well, let's make that 12 pi over 60, right? So that's pi over 60. So that's what we have to resolve. So if we do that, we can go back to our rectangular window resolution. Which is 4 pi over L. And say, well, I want 4 pi over L, right, to be less than my required frequency resolution. So that would imply what? That L is greater than, divide that out, pi divided by pi, so it's 1 over 60 divided by 4, so it would be 240. So let's suppose we're using radix 2 FFT, so next power of 2 would be 256. Suppose that's part of the requirement. But notice I kind of snuck this in on you. There's a magnitude part, right, of this. So it's not just a trivial extension of what we just did. Now we've got to sweat the magnitude. So is this even in fact resolvable? That's the next question, because we didn't even consider the side lobes. So let's kind of talk it through. This signal, you know, it has amplitude 1. There's no coefficient in front of it. It has amplitude 1. So let's convert that to dB in power. So it's 20 log of 1, 0 dB. But the next signal was 0.01 cosine 13 pi over 60. It has amplitude 0.01. Well, 0.01 is what, 10 to the minus 2. So the log of that's minus 2 times that, that's minus 40 dB, right? So this tells us, we know from our, I guess, that if this is 0 dB, that's minus 13 dB for the rectangular window, right? So the 0.01 cosine signal is basically not resolvable, or won't be visible. So it could very easily basically not be visible due to side lobes. So it's one of those things you have to watch when you're doing it, because it's not necessarily going to resolve it. You have to take care of your dynamic range. So I think, well, here is a good place to stop. And next time, we'll talk about the final exam and answer any questions.